Imagine a world where the fundamental building blocks of reality are not point-like particles, but tiny, vibrating strings. This is the world envisioned by string theory, a bold and ambitious attempt to unify the two pillars of modern physics, quantum mechanics and general relativity. String theory proposes that the universe in all its complexity emerges from the harmonious vibrations of these fundamental strings. Like the instruments in an orchestra, each string resonates at a specific frequency, giving rise to the diverse particles and forces that govern our cosmos. This theory, still in its infancy, promises to answer some of the most profound questions about the nature of space, time, and matter. It offers a glimpse into a reality far richer and stranger than we previously imagined, where extra dimensions curl up unseen, and where the fabric of space-time itself vibrates with the music of creation. The quest to understand string theory is a journey into the heart of the universe, a search for the ultimate melody that orchestrates the Cosmic Symphony. The idea that everything we see around us is made up of tiny vibrating strings is a radical departure from our conventional understanding of the world. Yet, it is this very radicalism that makes string theory so compelling. It challenges us to rethink our most fundamental assumptions about the nature of reality and to embrace a new vision of the universe, a vision where music and physics intertwine in a grand cosmic dance. The seeds of string theory were sown in the 1960s, a time of great ferment in the world of physics. Physicists were grappling with the problem of strong nuclear force, the force that binds protons and neutrons together in the atomic nucleus. Traditional approaches were failing to provide a satisfactory explanation for this force, and a radical new idea was needed. In 1968, Gabriele Veneziano, a young physicist at CERN, stumbled upon a mathematical formula that seemed to describe the strong nuclear force. This formula, known as the Veneziano amplitude, was initially met with skepticism as its connection to the physical world was unclear. However, it soon became apparent that this formula could be interpreted as describing the interactions of tiny vibrating strings. This realization marked the birth of string theory as a theory of strong interactions. However, the initial excitement soon faded as a more robust theory of the strong force, quantum chromodynamics, emerged. String theory was relegated to the sidelines, a promising but unproven idea. However, string theory was destined for a remarkable resurgence. In the 1970s, physicists realized that string theory could be reinterpreted as a theory of quantum gravity, a theory that could potentially unify the seemingly incompatible worlds of quantum mechanics and general relativity. This realization breathed new life into string theory, transforming it from a theory of the strong force to a potential theory of everything. At the heart of string theory lies a simple yet profound idea. The fundamental constituents of matter are not point-like particles, but tiny one-dimensional strings. These strings are incredibly small, far smaller than anything we can currently observe with our most powerful microscopes. Their size is estimated to be around the Planck length, a scale at which the very fabric of space-time is thought to become granular. Unlike point particles, which are characterized solely by their mass and charge, strings possess an additional property: their mode of vibration. Just as a violin string can vibrate at different frequencies to produce different notes, a string in string theory can vibrate in different patterns to give rise to different particles. The mass and charge of a particle are determined by the string's vibrational state. This elegant concept provides a unified framework for understanding the diversity of particles in the universe. All particles, from electrons and quarks to photons and gravitons, arise from the vibrations of these fundamental strings. The universe in all its complexity emerges from the harmonious interplay of these tiny vibrating strings. The idea that everything we see around us, from the smallest subatomic particles to the largest galaxies, is made up of tiny vibrating strings is both mind-boggling and inspiring. It suggests a deep underlying unity in the universe, a hidden order beneath the apparent chaos. It hints at a reality far richer and stranger than we previously imagined, a reality where music and physics intertwine in a grand cosmic dance. To understand how strings give rise to the universe we see around us, let's consider an analogy. A symphony orchestra. Each instrument in the orchestra produces sound by vibrating at a specific frequency. A violin produces a high-pitched sound, while a cello produces a lower-pitched sound. The different instruments, each vibrating in its unique way, combine to create a rich tapestry of sound, a symphony of music. Similarly, in string theory, each string vibrates at a specific frequency, giving rise to a specific particle. A string vibrating at one frequency might correspond to an electron, while a string vibrating at a different frequency might correspond to a quark. Just as the different instruments in an orchestra create a symphony of sound, the different vibrating strings in string theory create a symphony of particles. The forces that govern the universe, such as gravity and electromagnetism, are also thought to arise from the vibrations of strings. For example, the graviton, the hypothetical particle that mediates the force of gravity, is thought to be a string vibrating in a particular mode. In this sense, the universe is a grand cosmic symphony, orchestrated by the vibrations of countless strings. Each string plays its part, contributing to the overall harmony of the cosmos. In the early days of string theory, there were several different versions of the theory, each with its own set of strengths and weaknesses. However, in the mid-1980s, a remarkable breakthrough occurred. The discovery of 5 consistent superstring theories. These theories, known as Type 1, Type DIA, Type IYB, heterotic SO32, and heterotic E8, XE8, differed in their details, but they all shared the same basic principles. The discovery of these 5 superstring theories initially led to confusion and debate. How could there be 5 different versions of the theory of everything? Shouldn't there be only one ultimate theory that describes the universe? This puzzle was resolved in the mid-1990s with the advent of M-theory. M-theory, sometimes called the mother of all string theories, proposes that the 5 superstring theories are not actually distinct theories, but rather different aspects of a single, more fundamental theory. M-theory operates in 11 dimensions, one more than the 10 dimensions of superstring theories. This extra dimension allows for the existence of extended objects called branes, which play a crucial role in unifying the different superstring theories. M-theory is a highly complex and mathematically sophisticated theory, and many of its details remain to be understood. However, it offers a tantalizing glimpse into a deeper level of reality, a reality where the 5 superstring theories converge into a single, harmonious symphony. One of the most intriguing concepts to emerge from M-theory is the idea of branes. Branes are extended objects that can exist in multiple dimensions. They can be thought of as membranes or surfaces embedded in the higher dimensional space-time of M-theory. Our universe, according to M-theory, might be a 3-dimensional brane floating in a higher dimensional space-time. Other branes, representing other universes, might exist parallel to our own, separated by unimaginably small distances. These branes could interact with each other through gravity, potentially explaining the weakness of gravity compared to other forces. The concept of branes has profound implications for our understanding of the universe. It suggests that our universe might be just one of many universes, each with its own unique properties and laws of physics. It also opens up the possibility of extra dimensions affecting the strength of gravity, potentially explaining why gravity is so much weaker than other fundamental forces. The idea of branes, like the idea of strings, is a radical departure from our conventional understanding of the universe. It challenges us to rethink our notions of space, time, and reality itself. It suggests that the universe might be far more complex and multifaceted than we ever imagined. Despite its elegance and promise, string theory faces significant challenges. One of the biggest challenges is the lack of experimental evidence. The strings are so tiny that they're far beyond the reach of our current experimental capabilities. This makes it difficult to directly test the predictions of string theory. Another challenge is the vast number of possible solutions in string theory, known as the string landscape. The string landscape refers to the enormous number of possible ways to compactify the extra dimensions in string theory, each leading to a different set of physical laws. This raises the question of how to determine which solution, if any, corresponds to our universe. The lack of experimental evidence and the vastness of the string landscape have led some critics to question the scientific validity of string theory. They argue that a theory that cannot be tested is not truly scientific. Others defend string theory, arguing that it is still a work in progress and that it is too early to expect definitive experimental confirmation. The debate over string theory highlights the challenges of exploring the frontiers of knowledge. It underscores the importance of both theoretical innovation and experimental verification in advancing our understanding of the universe. String theory, despite its challenges, remains one of the most compelling and ambitious endeavors in modern physics. It offers a bold vision of a universe woven from the vibrations of tiny strings, a cosmic symphony orchestrated by the laws of quantum mechanics and general relativity. It challenges us to rethink our most fundamental assumptions about the nature of reality and to embrace a new vision of the universe, a vision where music and physics intertwine in a grand cosmic dance. Whether or not string theory ultimately proves to be the correct description of our universe, it has already had a profound impact on the world of physics. It has led to new mathematical tools, new ways of thinking about space and time, and new insights into the nature of gravity and quantum mechanics. It has inspired a generation of physicists to explore the frontiers of knowledge, to seek a deeper understanding of the universe and our place within it. The quest to understand string theory is a journey into the heart of the universe, a search for the ultimate melody that orchestrates the Cosmic Symphony. It is a journey filled with challenges and uncertainties, but also with the promise of profound discovery. It is a symphony yet to be played, a masterpiece waiting to be unveiled.